All right, welcome, 8th graders. Today we're going to be doing an ISN review for Life, the Universe, and Everything for Big Idea A of that unit. And this is an ISN that will hopefully be helpful to you if you've been missing and you need to get some notes, or perhaps you just want to make sure that your ISN is up to speed and everything is there. So we're going to start with question A1, which is all about galaxy types. And we're going to try to move through it fairly quickly so that you can get a quick review and hopefully get everything that you need. So here's a picture of our own Milky Way galaxy. This is what it appears from the surface without any telescopes. It's just a band of light that goes across the sky, kind of stretches across from one horizon to the other. And so to the ancient Greeks, it seemed to resemble milk, and so that's why it has that name. But every culture has a different explanation for why that's up there. There are some cultures that believe that that is the backbone of night, that it holds up the night sky, which is kind of a cool thing too. So you can see a couple different pictures there. Now, in general, what can we say about all galaxies, regardless of their type? Basically comes down to this. Galaxies are huge structures. They contain millions or billions of stars, sometimes more. Those stars orbit around the center of their galaxies, and that those centers have massive amounts of gravity at the core. Beyond that, though, then we start getting into more specifics. There are three types of galaxies: spiral, elliptical, and irregular. And of course, our galaxy type is a spiral galaxy, so we'll start with that. Spiral galaxies, these are some things that all spirals have in common. They contain equal amounts of gas, dust, and stars. They have a spiral shape, duh. And they're filled with lots of new blue stars. So a higher concentration of really large, hot, short-lived stars occur in spiral galaxies. And of course, you've got spiral arms in spiral galaxies, and this is where most of the gas and dust is located, and these arms slowly rotate around the galactic core, like in this little animation here, where we kind of fly around the center of the galaxy, and you can see the spiral arms and the individual stars and gas and dust that they make up. Some cool pictures of different galaxies. This is the Andromeda galaxy, which is actually about 2 million light years away from us. It's a spiral galaxy, part of the local group. Here's a picture of another galaxy. Another thing of interest is that these spiral galaxies occur along flat rotating disks. So we call that flat disk part the galactic plane. So if you were to look at a galaxy from the edge, you wouldn't see this. You'd just see this very thin amount of material, the disk itself. Here you can see the galactic plane of a galaxy. And so it's very, very flat. And here's another galaxy seen edge on, the spiral galaxies with their flat galactic planes. And then, of course, you have the galactic core at the center. There are millions of stars, massive amounts of gravity, and lots of X-ray energy coming from those as well, which is kind of interesting. So here's, I believe, an artist drawing of a galactic core. Here's an actual photograph of the core of a galaxy, the Whirlpool galaxy. Here's another cool spiral galaxy with the spiral arms almost obscuring the central core. And this is a cool one too, of the center, the core of a galaxy. The part you see here on the right is just this little tiny square photographed right there. Here's another spiral galaxy picture, and another one, and another one. This one in particular I really like. It's the Sombrero galaxy, and it's a very unusual galaxy in that it has really no spiral arms. It's just one giant flat spinning disk. And the name, let's be honest, is kind of cool too. One special thing to note about spirals, that about half of all spirals are known as barred spiral galaxies. They have two spiral arms and this bar-like structure, which you can see in this photograph right here. And the reason I bring this up is because the Milky Way is actually a barred spiral galaxy. And of course, in this little area right here, you can see the photograph. And you can see lots of other galaxies far, far in the distance beyond and behind this spiral arm right here, just to give you some size of the scale. And of course, here's another barred spiral galaxy. And so moving on to elliptical galaxies. What is there to know about elliptical galaxies? Well, obviously they are oval shaped, as you can see right here. Ellipse is the fancy name for an oval. And so elliptical galaxies typically have an elliptical or an oval shape. What are some other things that is common about them? All ellipticals have no spiral arms. They're mostly old, small, cold stars, which is also kind of an interesting trend. And they have very little gas and dust. They're mostly all stars, hence this kind of fuzziness to them. A few other things. These stars, the stars in an elliptical orbit in an ellipse, but not on a flat, organized plane. And they produce lots and lots of X-ray energy too, just like the spirals do. And so moving on to the irregular galaxies. Here, the name pretty much says it all. Irregular galaxies have irregular shapes. No two are exactly alike. And there's an irregular galaxy. It's actually a dwarf galaxy. It's a small irregular galaxy. So other things that irregulars have in common, they contain almost no stars. They're virtually all gas and dust. And obviously, as the name suggests, they don't have a regular shape. Some speculation about what might be causing this. Scientists currently believe that these irregular galaxies are the result of galaxy collisions. That you'll have two spiral galaxies, for example, in this simulation, approaching each other, and that their gravitational interactions with each other distort, change their shapes, and turn them into irregular galaxies. Which is kind of a cool thing when you consider what's at work here and what's really at the center of these galaxies. With all of that gravity, these two galaxies are in a dance, and they're going to eventually merge together. But in the meantime, it creates a lot of chaos. It creates a lot of these irregular shapes. And so what you're seeing in the simulation might really resemble some of the pictures that you've been seeing recently in some of the prior slides. And then so to wrap things up, just to give you some specifics about our own Milky Way galaxy. Our Milky Way is located about 2/3 out from the center of our galactic core, which is a good thing. It's not necessarily good to be in the center. Our solar system orbits around our galactic core. It takes about 250 million years to make one complete orbit, which with a star that's only about 4 or 5 billion years old, that means maybe about 12 to 15 orbits total since our star first formed. So it's a big distance that we have to cover there. It takes us a long time. Last little tidbit of information, our own galaxy is about 100,000 light years across and about 1,000 light years thick, as you can see from that photograph. And so that's the galaxy type review. That would be question A1. I'd also like to show you some A2 stuff here. So we're going to jump in with this show, and we'll just cover what's at the heart of galaxies and whether or not there are black holes at the center of all galaxies. So a couple quick definitions that are important to know. There's a distinction between the stellar mass black hole, which we learned about back in star stuff, and that's your typical 3x, maybe even a 4x, all the way up to a 10x star that's gone supernova. But what we think is at the heart of a galaxy is far, far different. That's a supermass black hole, which would be a black hole that's millions or billions of x's or solar masses, so on a completely different scale. You can see some animations here that are likely to play in front of you. Here's a big, huge 3x blue star that's being pulled apart, spaghettified, by the supermass or by a regular mass, stellar mass black hole at the center. You can see the accretion disk forming around here, and you can see the event horizon as part of that too. And here you can see some more interactions where a star is getting close to a galaxy, or close to a black hole, and it's going to end up getting spaghettified as it gets in closer and closer. And part of the coolness of this is that you get to see the accretion disk that gets created when this sleepy black hole ends up consuming the star material, and then it becomes a hungry black hole. And so we can see that right there, the accretion disk forming. And you can also see the event horizon there in the center as well. That would be that black area. And then here's just one more animation showing a star orbiting around a black hole, being spaghettified, pulled apart, and being added to the accretion disk. What I like about this animation is you actually get to see the X-ray burst that's caused by this material falling into the black hole, which is something that previous animation did not show. So I think we're due for that X-ray burst right about now. So those add to some of the telltale signs of a black hole. Also, don't forget to have spaghettification in there. Spaghettification is the stretching and the tearing apart that you would experience next to a black hole because your feet would be getting pulled harder than your head. A very uncomfortable position to be in. And then to make the case for black holes being at the center of galaxies, here you can see the galactic core. And here you can see a picture of the center or the core of a black hole. And you notice the structures are identical. And even down to this central region right here. So we see the same structures. And what's also of interest is, besides the accretion disk showing up here in the galaxy core, you also see the X-ray jets, which you typically get with a black hole. And so those are the telltale signs that you have a black hole at the center of that galaxy. Here's another accretion disk photograph from the center of another another galaxy. Here's another galaxy, and again you get that accretion disk shape. Here's a little animation showing what you would find at the heart of a galaxy. As you fell into it deeper and deeper, what you would eventually come face to face with would be the accretion disk and eventually the X-ray jet pouring out of the center of this thing. So that's what we think lies at the center of all of these black holes, or all of these galaxies. And so let's make a case too for the X-ray jets. Here's what we think a black hole looks like with the accretion disk and the X-ray jet. Here are two galaxy pictures. This one over here is one of the farthest galaxies ever photographed. And you can see the X-ray jet shooting out of that, and you can see the X-ray jet here coming out of this galaxy. Here's another galaxy seen with X-rays, and you can see the X-ray jet shooting out of that galaxy. Here's another series of pictures with an X-ray jet coming out of this galaxy. And here's a quick animation zooming into the center of the Milky Way galaxy, and you can see the X-ray sources at the center, and you can see when you combine the X-ray pictures with some of the visible light pictures that there's a lot of X-ray source at the center of this galaxy, which again would make you say black hole, because black holes generate these large X-rays. Here you can see a picture of the Andromeda galaxy, here with all sorts of different things combined. The visible light version, the infrared or heat version, the X-ray version. You put all of that together so you can see all of the different pieces, and the X-ray, telltale X-ray jet at the center. Here's a galaxy that actually has two X-ray sources with two X-ray jets. So sometimes galaxies are merging together while we photograph them. Here you have two supermass black holes about ready to merge inside of that galaxy. And that's what galaxies do. They combine with each other, they crash into each other, and eventually those two black holes end up becoming merged and become even bigger, larger and larger stellar mass black holes, or supermass black holes, excuse me, forming from the combination of these two. And then just to wrap up, here we have a photograph of the center of our galaxy with at least 4 identified supermass black holes near the center of our galaxy, dancing around each other, getting ready to merge into something quite a bit larger with much more gravity. So just to summarize, what is it that black holes and spiral galaxies in particular have in common? They both have high amounts of X-rays near their cores, as you've just seen. They both form these flat spinning disks. In the case of a black hole, we call it an accretion disk. In a galaxy, we call it a galactic plane. It's probably the same thing. And both have extremely massive cores with high amounts of gravity. And I guess the problem is, if it's not a black hole, we have to somehow explain how all that gravity is there in the center of that galaxy without it being a black hole. And there really is nothing as massive as a black hole in there. So it almost has to be that. And that wraps up questions A1 and A2. And we're down to about the last minute of recordable time that I have here. And so what I'm going to do is I'm going to pause, and if you'd like to come back and see questions A3 through A5, we'll do that in another video cast. Until then, I'll see you later.